Hey guys, welcome back to my channel. Yesterday there was a bit of problem. I think I uploaded the day 19's video instead of day 20. Um, but there were not many views, so I hope you guys are okay with that. I uploaded the correct video just now. And today for this video, I'm gonna upload uh, the the additional part of the DFS, and I'm going to solve one quick question in terms of DFS. Just one second. Yeah. So yesterday we talked about DFS as in the general terms like nodes, trees, branches, um, so on and so forth. Um, Today we're going to discuss three types of DFS, which is pre-order DFS, in-order DFS, and post-order DFS. So by pre-order DFS, um, the logic is that it is done on the current node before moving on to the children. So as you can see from the name already, pre is before, in order is in the middle, and then post is after. So let's say we wanted to just print the value of each node in the tree. Then at any given node, we would print the current node's value, um, and then recursively call the left child, and then recursively call the right child. So I'll show you guys this with the code. Let me share my screen really quickly. Yeah, so as you can see from the uh, code pre-order DFS, so you first check if the node is not empty, and then you recursively call the left node first, and then you exhaust all the nodes on the left, and then move on to the right side. So because logic is done immediately at the start of each function call, and pre-order handles nodes in the same order that the function calls happen. So yeah, it goes same for the in order DFS. So we first recursively call the left child this time, um, then perform logic on the current node, and then recursively call the right child. So as you can see, the print is in between the left and right, which means that in the middle, you just already call the current node. So that is the difference. I didn't write the code for post order DFS, but I think you guys can already guess that we recursively call on the children first and then perform logic on the current node. So no logic will be done until we reach a leaf node, since calling on the children takes priority over performing logic. So the root is the last node. That was it actually for the theory. Let's try to solve some question. Um, so yeah, maximum depth of a binary tree. Given the root of the binary tree, return its maximum depth. Maximum depth is the number of nodes along the longest path from the root node down to the farthest leaf node. As you can see from this binary tree, the output is 3 because uh, yeah, from 15, this branch, 1, 2, 3, and then you can already see that the longest path is 3. Um, Yeah. Oh no, the root is given here. Sorry, my bad. So you first specify the root and then it's gonna give you the output. 3920. Yeah, yes. So well, how are you gonna approach this? So basically, let me visualize this. So given number of nodes like this, on the top there's a root node. Mm, yes. So how we do this is basically we call the root node first, and then because we iteratively start with the left node, we're going to move on to the left node to count the distance. So the logic will be um, we calculate the path of the left side and path of the right side, calculate the maximum of those two, and then add one. The reason why we add one is because um, when we're comparing the difference between the nodes, we don't add up the root node. So root node is not considered yet, so that's why we have to add one. Um, so if we apply that logic here, left is one, um, but we don't know the one down here yet, right? So we have to go down to the maximum depth of this node. So in this case, we don't have, this is a leaf, no, this is not a leaf node, but there's no left or right children node. So that means right is zero, and it's also for the same, left is zero. So the maximum of this zero and zero is zero, but then we haven't considered the root node yet, so we have to add one. So the parent node, which is this node, is the value of this node is one. Now we move up a node, and then for this node, we already know that the left side is one because we just calculated. And how about the right side? We don't know the right side, so we go to the right side. We call the function in this case. For this one, for right node, we don't have the left node or right node as a children node, so that's also L equals zero and right equals zero. Maximum of zero and zero is zero, and then you add one to it, so that's also one. Now you have the left one and right one for its parent node on this level. So the maximum of one and one is one, and you add one to it, so that's going to be two. And you move up a node, but this is a root node, so now we call the left side is on, so now we call the right side. We go down, left node is zero because there's no left children node. Well, to call the right node, we have to go down the children node. And then for this one as well, left is zero. But and then we call the right node, right child node, which is this one again. But left is zero again, right is zero again. So this becomes one. We move up a level. Right is one, left is zero. So this is maximum of zero and one, which is one plus one is two. Right is two, left is zero, maximum is two, plus one is three. And then with the same logic, this not the same logic because now we have to check the left node, which is 2. There's 2 and 3, and the bigger one is 3. So we go with 3, but this is a root node, so you have to add 1. So this will be 4. So that's like the logic behind the code. Um, Recursively implementing a code is actually pretty simple. So what you do is um, you first define the logic of left node and right node. So we're first assuming that whatever function call that we're going to do is going to solve our um, base method. So that will be self dot max depth root dot left. Right is self dot max depth root dot right. And now we have to set the edge case. So what was the edge case for DFS again? That's if not root, then return 0. Okay. So yeah, we call the left node first, and then after the left side is exhausted, we also call the right side. And then what we also do is return, the logic is return the maximum of left node and right node, which will be left and right. And then we add +1 to it, right? So let's see if this works. Yeah. So as you can see, if the root is 3, 9, 20, no, 15, 7. So we're just visualizing, we visualize this node as this uh, graph here. So that's 3. And for case 2, this is also correct. 3, 9, 20. Yeah. No. Yeah. Well, yeah. So that was it for today. Um, there's a lot still left for graph theory, so I'm gonna study that more in the upcoming days. And yeah, stay tuned. And if you guys have any comments, let me know. See you guys tomorrow.